Hello everyone, welcome Changsheng to the IAS. Changsheng is a presidential young professor in the Department of Materials Science and Engineering at the National University of Singapore. He's one of the upcoming young professors and one of the leaders in some of the wearable technologies and wireless technologies that he'll present today. So he focuses on developing wireless wearables and intelligent robots for energy harvesting, biosensing, and therapeutic applications, working on bioelectronics, material science, and advanced manufacturing techniques to create them. So we first met in 2018 when I visited Professor Zhong Limang's lab in Georgia Tech for a 2-week period, and then we became friends afterwards. And then maybe within the last 4 or 5 years, in 2 or 3 conferences we met, we had discussions, we exchanged ideas on collaborations, and then I thought this is the perfect time to invite Changsheng to come and work with us, because soon we'll be starting the SUSTECT Vice Chancellor's Research Cluster, where we will be focusing on next generation wearable technologies, how we can integrate different sensors and different technologies with wearables. And with his expertise, we expect to collaborate on a large different number of areas. And with this visit, he'll be able to talk to many academics in Loughborough and then further those collaborations as well. So welcome, Changsheng, and over to you. Thank you.
Thank you, Isha, for a very kind introduction, and also thank the IAS for a generous support. It's really my great honor and to be here, and also this is my first time in UK, so which makes this opportunity even more special. So, as Isha mentioned, I'm currently an assistant professor in National University of Singapore, NUS, and I'm also holding courtesy appointments in electrical and computer engineering because of the research I'm doing. So today I'm going to share some of our recent works in the area of wireless wearables with the goal of pervasive healthcare. To start with, it's just a little background. And today I understand that we have colleagues from all different areas today, so I will try my best to make my contents to be as interesting as possible. All right. So here are some general backgrounds. I think everybody are having experience with. So especially in Singapore, the whole society are facing issues from climate change, global pandemic, and population aging. Like for example, climate change, because Singapore is already in the equator, and we only have summer. So that's why I'm so happy to be here in the autumn season, right? So I can see different colors of the leaves. So, but climate change really have a huge impact in Singapore because the sea levels will affect the area, the country has, and also because it will further elevate the current high temperature already in Singapore. And we know that heat will actually affect human performance and human health a lot. And that's why in our university, we have like Heat Performance Resilience Center, which was just established 2 years ago to study the effects of thermal stress on human potential and performance. Global pandemic, I mean, no need to mention, right? We have been experiencing the influences of COVID-19 pandemic in the past few years. And for population aging, that's another big topic in Singapore, because by the year of 2030, it's expected 1 out of 5 of the population will be elderly people beyond 65 years old. That's a large population. So all these things are causing great burdens on the medical systems and the resources. So that's why, together with other societies over the globe, people are trying to transform existing clinical practice, which currently are centralized, intermittent, and curative. That means we only go to see the doctor in the hospitals when symptoms show up. But in an era of digital health, we would like that practice to be changed, to be something that's more pervasive, continuous, and predictive, right? So we can monitor our health without a hospital visit and can predict the onset of symptoms before it actually shows up, so that we can easily tackle these medical conditions before it gets more complicated. So to achieve that, it calls for interdisciplinary research efforts from many different diverse fields. In my group, we try to frame the problem into a design framework, what we call WISE. So we want to improve the wearability, the inclusivity, the economy, and also sustainability of existing medical instruments or medical devices, so that we can easily deploy them on large scale in and pervasively in daily off-hospital settings. So that's why. So my current group research actually focus on two important aspects in that bigger design framework. The first part is sensors, because the sensors basically acts as the 5 senses of the IoT devices, right? So it provides the senses or functionalities for health monitoring. And we are working on how to enable more advanced sensing modalities, and also how to achieve better sense making of collected data. And the other aspect is the energy part. So all sensors or electronic devices relies on energy or electricity to drive them. It's like the heart or blood to drive out the blood flow in our human body. So for the increasing number of medical devices we are going to deploy in the era of digital health, that means we will require a large number of distributed power sources for them. And how to integrate these power sources seamlessly with our human body or with existing wearable device clothes or devices, that will be something very important for us. Of course, currently another thing I would like to mention is because I have more background in electrical and mechanical engineering. So currently our research mainly focus on the interaction between physical fields and materials. So we haven't going that deep into chemistry area yet. But I think biochemical sensing are definitely exciting field to further expanding the field of wireless wearables. Yeah, so to start with, I'm going to introduce some of works and the recent efforts in how to improve the wearability, inclusivity, and the economy of existing wearables. So the wearability means the comfort. The inclusivity is we want something that's easy to operate, and so that normal people can use the device just as the skilled personnel in hospital do. And the economy is we want to make them low cost so that people can afford it, because we know a lot of the medical instruments in hospital cost a lot. So the first work I would like to introduce was can be dated back to my postdoc period when I was in Northwestern University working with Professor John Rogers. So we were approached by a group of pediatricians. So they have a clinical need. They want to monitor the brain oxygenation in pediatric patients, because they see patients in ICUs, they see patients with neurological diseases, which may experience insufficient blood supply into their brain. And this will cause permanent head damage or even sudden death. So it's very important for them to monitor the blood supply and also the oxygen saturation levels inside the patient's brain continuously. Conventionally, we can only do it with this kind of tethered system, and such a system costs really a lot. But for many of the patients, especially the kids, they a home's environment is much better for their growth and for their interaction with the family. That drives us to develop this kind of wireless miniaturized near-infrared spectroscopy device. So it operates on the near-infrared spectroscopy and which measures the optical properties of tissue for hemodynamics monitoring. So the key points here is we try to minimize the cost so that the device is only costs several $100s instead of thousands or tens of thousands of dollars. And another thing is we want it to be extremely soft so that it can go gently onto the sensitive skin of neonates. And the other thing is it needs to be small and lightweight so that they don't feel a burden to wear it. Right. So, and also we want it to be wireless so that there's no tethered wires to affect the interaction between the neonates or kids and their parents. So what we did is we rationally designed the whole entire circuit boards so that even though we are still adopting the high performance microelectronic components, we can achieve structural stretchability through mechanical design, like using this kind of serpentine interconnects. So we are effectively dividing these rigid components into several islands, and the serpentine interconnects allows us to achieve structural flexibility so that it can be easily bent or twisted and can conformally adapt to the sensitive skin of the patients. So here is a closer look at the sensor design. So it's actually pretty straightforward. We have the light sources and also the photodetectors. So the light sources we follow the convention in the field and use the red light and near infrared light at 740 and 850 nanometers wavelengths. But on the photodetector side or the sensing side, we adopted a linear array at different distances from the light sources. The purpose of that is to enable us to sense different the information from different depths, because based on the optical simulation using Monte Carlo algorithms, we can see that the further the distance between the source and detector, the more light ratio we can pick up from the deeper tissues based on the simulation results here. All right, so we can see here, so with the further distance, we can have more light ratio coming from the deeper gray and white matter. So with that, we will be able to decode different physiological signals from a single device, what we call multimodal sensing. With the shorter distance pair of photodetectors, we will be able to capture the peripheral oxygenation and also heart rate because of the positive waveforms. Then with the larger distances, we will be able to pick up the cerebral information like the oxygenation and also the vascular tone from the device. With all this, we continue to validate such a platform on real patients. In this case, the kids with CCHS, which is congenital central hypoventilation syndrome. So for these patients, their nerve system is incapable of picking up the event of insufficient oxygen in their brain. So they will not be able to sense the lack of blood supply in their brain. So in that case, the sleep can be quite dangerous for them, because if they are, for example, their airways are blocked, or their mouth or nose are blocked by physical subjects, they will not be able to sense it, and they will experience a constant drop in their brain oxygen saturation levels, and that will cause them to experience head damage or even sudden death. So they really need a continuous monitor for their brain. And conventionally, patients can only do it in hospital, right? So we can see all these kind of instruments on their brain, and but with our device, we hope to achieve at-home monitoring so that they do not need to have frequent hospital visits. So first, in order to validate it, we conducted some lab tests on these subjects. So the first one is head-up test. So normally, if we start with a horizontal position and we suddenly tilt the participants up, because of gravity, there will be a drop in the blood supply into the brain, and we can see a drop in the brain oxygenation percentage. But for these patients, because they will not, their nerve system will not be able to pick that up, so there will be no regulation of the blood supply to pump more blood into the brain to compensate that drop. So this drop will be constant and stay, their brain oxygenation will stay low there without recovery until we tilt them back to the horizontal position. All right, so we also conducted more hypoxia tests to see how our devices perform compared to the gold standard commercial tested systems. So we realized that the wireless platform actually gives us pretty good accuracy in comparison with the gold standard results. So that's why currently we are conducting at-home test clinical trials to see the efficacy and the usefulness of the platform in home settings. Based on similar technology of near-infrared spectroscopy, we can also monitor the oxygenation at other tissue or other body locations, right? So another typical example is plastic surgery. So for plastic surgeons, when they do the free flap transfer, after the surgery, they need to monitor the health status of the transferred flap. And in the United States, the gold standard is the tissue oximeter, which is shown on the left side. So this tissue oximeter also works on the principle of NIRS, and it measures the optical absorption changes to reflect the blood supply or blood perfusion in that transferred flap. Right. So if we see a sudden decrease in the tissue oxygenation, then we know there's some events ongoing, either it's ischemia or congestion. So we customized our device for that purpose to make it fully waterproof and also with longer battery life. Because for the flap monitoring, it usually takes about 5 to 7 days. So that's why we customize the device to fit the needs of the plastic surgeons. And we first conducted animal model tests to validate the effectiveness of such a platform. And we can see for both ischemia events and the congestion events, the wireless device will be able to pick up the changes in oxygenation similar to the gold standard commercial instrument. And remember, our wireless devices are just tens or hundreds in terms of cost compared to the commercial instrument. And currently, we are also running human clinical trials in hospitals to see the long-term stability of such a platform when it comes to 5 to 7 days continuous monitoring. Probably a more interesting exploration we are currently working on is for at-home mental assessment. So conventionally, people have been doing fMRI to assess the blood flow in the brain. And that's great. That's a great technology, gives you a very high resolution and also very fast higher resolution in both time and space, right? So, but the problem is we cannot do MRI every day. That's going to be insane, right? And also, MRI is a very expensive instrument. So that's why psychiatrists actually they have been looking for other technologies, including functional near infrared spectroscopy. So the way it works is it uses similarly it uses optical absorption to detect the changes in the blood flow in different brain regions. Of course, it's a much lower resolution compared to MRI, but it is still with a sufficient number of channels, you still will be able to do a mapping of the blood flow in the entire brain region. Of course, conventionally, people have been using this kind of bulky and of course FNIRS system, like from Hitachi. It has many channels, 52 channels over the head. But the problem is, it takes 1 to 2 hours just to mount the helmet. You can imagine you need to carefully put the probe, optical probes through the hair and stick it to the scalp, right? So it takes a long time to just mounting the device, and the whole test probably just takes 5 to 10 minutes. So it's really difficult to do such tests for regular patients and on a large scale. Recent years, there are another company, RB Lab, they come up with a more wearable device. So instead of trying to cover the entire brain region, psychiatrists have figured out that actually the prefrontal cortex matters more when it comes to mental awareness. So it's especially when it's on the participants are challenged by cognitive tasks. So they designed their system to be focusing on the prefrontal cortex, and greatly simplifies the device design, also the difficulty in deployment. But still, it costs a lot. It reduces the price to 500K to 100K, but it's still way beyond the affordability of normal families, right? So the motivation for us is to develop a really low cost wireless miniaturized device. I will not say achieve 100% of what we can do here, but we can do at least 80% of it. Then, but just at a very small fraction of the cost, so that we can deploy the devices or the technologies to more families on a large scale. And some participants will be able to do this kind of home mental assessment at home. So so that we can deliver better precision medication for them. So after customizing our platforms for that need, we have to do some validation tests. So the cognitive task we adopted is verbal fluent task. So what we did is we just asked the participants to spell as many words as possible, starting with the letters we give them. So they are challenged by the task, and they have to think, and then that will drive, ask the nerve system to drive more blood into their brain. Then we will be able to observe the changes in optical absorption. All right. So we can see here for the first subject, during the VFD test, we see a quite drastic change, especially the difference between the concentrations of different types of hemoglobins. The HbO2 here represents the oxygenated hemoglobin, and the HHB here represents the deoxygenated hemoglobin. So here we can see, obviously the nervous system is pumping more blood into the brain, especially from the artery. That's why we can see an increase in the oxygenated hemoglobin concentration. But and relatively, the deoxygenated hemoglobin concentration will drop. So this results matches very well from the 100,000 instrument, right? So we can see this is their results. Of course, we did multiple rounds of tests, and they all show similar results from this subject. And let's look at another subject. So for this subject, it's less focused on the task. So we can see instead of pumping more blood into the brain, we can see the oxygenated hemoglobin concentrations actually drops. Okay, so this pattern matches very well from what we observed from the much more expensive commercial instruments. So this allows us to build a confidence in such a platform, and currently we are running clinical trials on real patients with ADHD and or depression. Yeah, so we are currently running trials on this. So let's what I've talked about is about optical sensing and how we are trying to transform existing bulky, expensive NIRS system into more wearable miniaturized form, so that we can adopt them for different applications in ambulatory settings. Another technology or platform I would like to introduce is about mechano-acoustic sensing. It also starts back in the days when I was a postdoc, and when a group developed this kind of miniaturized mechano-acoustic sensors that can capture the subtle vibrations on the human skin. And especially if it's, for example, if it's mounted onto the suprastal notch, where multiple different types of sensors intersect, it can actually pick up multimodal mechanical information from the human body, including, for example, vital signs, heart rate, respiration rate, and unconventional biomarkers, including coughing, speech, sleep dynamics, and also even swallowing. Right. So during COVID pandemic, I mean, we really cannot do much. So so instead of just playing video games at home, so we think about, well, why don't we deploy the device onto the to the patients and the nurses or doctors. So what we did is to mass produce this exactly same device, and we start a deployment onto a large number of subjects, including patients, nurses, and physicians, and we collected tons of data. And the biomarker we are trying to detect is actually coughing frequency. So that's something, because based on our conversation with the physicians, that's something they actually are very interested in. But so far on the market, there's no existing solution to continuously monitor the cough counts. Usually when we go to see a doctor, we just tell them how frequent we in a rough idea, right? But when it comes to kids, then it's even more challenging. They really don't know how to express the coughing counts or frequency. So it will be nice to have a quantitative measurement for this kind of coughing frequency, because it reflects the recovery of COVID-19 and some other diseases. But when we, so for example, when we look at the raw data of such a mechano-acoustic device, the only thing you can see is some of the acceleration data, right? So from the skin vibrations. How are we going to classify all these different events from this noisy acceleration data? That's something requires advanced analytics. So the most intuitive way to do that is look at the frequency spectrum, right? So of course we can do the spectrum analysis, and then you can immediately notice that some of the events actually have quite different, distinct frequency attributes from other events. For example, the heart rate and respiration, they usually have their own frequency range in 1 hertz or even less than 1 hertz, right? So, but for speaking, is and coughing or laughing, all these events, they have quite broad range spectrum. So covering from fundamental frequency, probably like 80 to 100 80 to 100 hertz to all the way up to 1000 hertz. So how are we going to differentiate these all coughing-like events to achieve accurate biomarker detection? We need to go beyond these kind of frequency spectral diagrams. So that's where deep learning or AI algorithms comes in. So what we did is we first pre-process the data into using wavelet transformation. Then with this kind of spectral diagram, we will be able to feed them into a convolutional neural network and trying to identify their unique features and then classify this kind of events from this noisy acceleration data. So from there, we will be able to do continuous monitoring of all sorts of biomarkers with pretty high accuracy. So for example, the top plot here presents the coughing counts every 5 minutes, and we can see clearly how the coughing frequency changes during the day, and also the speaking frequency, the physical activities, all just from a single device on the throat. But back then, after we resumed the work during the COVID period, another colleague of mine, Dr. Xiaoyue Ni, currently at Duke, we were thinking, instead of just measuring a single point vibration, can we do more if we can measure the vibrations at multiple points simultaneously? And that's what drives us to look into this kind of wave propagation. So if we will be able to measure the vibrations simultaneously at 2 different locations, then naturally we will be able to pick up the surface wave propagation on that surface. And based on wave theory, that wave property or the phase velocity actually highly correlates with the mechanical properties underneath the surface, right? So by measuring the dispersion relationship between wave number and the frequency, we will be able to estimate the stiffness or elasticity of the materials underneath the surface. That's actually quite relevant in biomechanical field, because people are always trying to measure the stiffness of the organ inside our body. And conventionally, people have been doing it using ultrasound elastography or optical coherent tomography or OCT. So these technologies are great because they gives us very high resolution mapping of the phase velocities, of the wave velocities in the region of interest, and it gives us, so that's why we can do ultrasound imaging, right? So we can go to hospital and take ultrasound images to see babies, fetus, and to see whether there are tumors or to see how the body changes. The problem is all these technologies require skilled personnel to operate, and it's super expensive. And these instruments can only be afforded in larger hospitals. But there are also other scenarios. We do not need actually this high resolution mapping of the muscles or organs. We are just interested in the dynamic properties, how things change during our daily activities, for example, for rehabilitation, right? So we are more interested in the dynamic responses of our muscles during exercises, during daily in daily settings. So in the past couple of years, of course, people have been pushing this field by developing wearable ultrasound patches, for example. And these are great in the sense that it offers a much more miniaturized system. But still, with these ultrasound patches, the high power consumption and also high computation cost associated with ultrasound signals makes them very challenging to deploy during dynamic motions in real time. So that's why we developed this wireless mechano-acoustic wave sensing device with just two simple high fidelity, high broad bandwidth motion sensors that what also we call inertial measurement units. So these are just motion sensors that still measures the acceleration or vibrations on the skin. Okay, so we couple them with a vibration actuator, which is a small speaker. So it generates the sounds or the vibrations on our skin. And these waves will propagate through our skin and picked up by our mechano-acoustic wave sensor. So we designed it in a way so that it's very compliant with the sensing elements electrically connected to the MEMS circuit boards, but mechanically isolated from the rigid parts, right? So these serpentine structures makes them really soft, so you can easily deploy them onto almost anywhere of the body location, and also you can easily bend or stretch, twisting them. So based on the feedback of our subjects, they say they can barely feel it, even after we mount the devices onto them. So the whole idea is we will be able to generate the vibration, and our sensors will pick up the vibrations, and through the analysis of the dispersion relationships, we will be able to decode the stiffness of a muscle underneath the skin, even during dynamic motions. All right, so probably I'll just go through briefly on the physical underlying mechanism part. So of course, since we only have two sensing elements, we have to make assumptions and simplifications. The simplification we adopt is we just view the whole tissue to be two layers. One layer to be skin fat, the other layer to be muscle organ. Of course, with ultrasound and OCT, you can do a high resolution mapping, but with just two sensing elements, that's what we can do with for two layers. So the idea is we want to calculate the aggregate stiffness of the top layer and the bottom layer. And also, what will be of interest is the thickness of the top layer, right? We want to know where the boundary is in order to properly describe this kind of tissue stiffness model. So the idea is we use the finite element analysis to derive a scaling law for such a model, so that based on the sorry, I think the resolution of the picture, so for some reason is very low. So so that we will be able to, based on the dispersion relation curve, we will be able to inversely estimate the three parameters I just described: the stiffness of the two layers and also the thickness of the first layer. So a simple observation here you can see from the scaling law, which is the right plot layer, is that if the wave frequency is high enough, that means the wave length is small. So this for this surface waves, they will mainly propagate in the top layer because their wavelength is so small, and they will not be affected by the interface and the bottom material. So that what we measured, so whatever velocity we measured at a high frequency region is only related to the top layer. So give us a very simple method to estimate the stiffness of the top layer directly. No need to do FEA, no need to do optimization. We know immediately we will know the first layer property. And then that reduces the unknowns to just 2 parameters and reduces the efforts to inversely estimate the bottom layer material property and also the thickness of the top layer. I'm going to skip the details there. And what we did is first we try to validate the method and the platform on phantom materials with just two different layers of with just 2 layers of different silicone materials. And there's a combination of 19 different materials. And here we plotted like 10 of them. And based on the dispersion plots at the top, we can see our estimated values of the stiffness actually matches very well with the gold standard measurements, which is from the tensile stretching test. All right. So what's more important is here we do not need to do any calibration. So these results are directly output from our algorithm because we are also using wave theory. So the values the values we obtained are absolute values. Of course, it's estimation, but it's still absolute values. We do not need to do calibration against gold standard measurements in order to get these reasonable results. So then we further did that on synthetic tissues that we're trying to simulate the case of skin cancer, right? So with skin cancers, the stiffness of that region will change. So in this case, we just dig a hole and fill in different materials with varied stiffness, right? So we can see the estimated the estimated change of the materials embedded, and the relatively stable values of the underneath the second layer. And we also conducted in vivo muscle stiffness measurements. So the subject hosts different weights, and we can from the ultrasound elastography we can see how the velocity mapping intensifies, and you can see red colors means higher phase velocity and also higher stiffness. And using our own device, we can also see the similar increase in the muscle stiffness, and these values are uncalibrated raw value, raw outputs from our estimation algorithms. And then what's more interesting is we can finally do continuous measurements during dynamic motions. And in this case, the subject is doing cyclic lifting. All right. So in this, with our platform, we will be able to continuously measure the shear wave velocity and also estimate the stiffness of the muscles in the biceps. So let's look at the video here. So you can see at the different postures, this is how the modulus changes. And you can do continuous measurements of the stiffness, muscle stiffness. Yeah. And these are what we have done in the past on the wireless miniaturized device. But then how can we make such devices even more comfortable? Right? That's always a question asked. And especially in Singapore, when it comes to skin patched devices, people complain. They say, I'm sweating, and these patches, even though they are soft and flexible, is still causing excess heat and also making me uncomfortable with all the sweats. And also, the sweating and the high humidity environment makes them very difficult to ensure intimate contact between the device and the skin, and effectively dropping the accuracy and reliability of the measurements. So it will be great for us to have contact-free sensing, right? Especially if we can, as what is just mentioned, it will be great to have smart textiles that we have all the sensing modalities implemented in our clothes instead of onto our skin. So electrical engineers have been thinking about that and working in the field for quite some time. And for example, there are several kinds of wide area sensors. Here, in this case, people are using Doppler radio frequency sensors that will be able to pick up also the vibrations of our human skin or our motions, so that they can decode the physiological information from it. But obviously, there are drawbacks. With this kind of wide area sensors, with all the things going on in the room, especially nowadays with all the wireless devices, phones, earphones, and also Wi-Fi's, such measurements are prone to environmental interference, and you may not be able to get continuous measurements and reliably. So that's why one of my previous colleagues at NUS, Professor John Ho, he has been quite creative in creating this kind of radio frequency localized sensors. So instead of having these wide area sensors, what he tries to do is design different RF metamaterials and integrate them into all sorts of textiles. For example, the seats and the seat belts. So when you integrate all these RF metamaterials to these stationaries, right? So then it ensure for these cases, we still have close proximity to the human body, but we still will be able to sense the vibration and motions of a human body in a contact-free setting. But still, it solves the problem issues with this kind of wide area sensors by going into a more design perspective, but still it requires bulky software-defined radio instrument that actually will be used to pick up the data from these kind of antennas, right? Because so that's why all previous works, they all designed to be on the stationary furniture or seat belts, where they can easily connect to a bulky SDR instrumentation. Can we make it smaller, right? So it's a natural question we ask. So what we want to do is to address the environmental interference and also reduce the reliance on bulky instrumentation for data acquisition. And with all that, then we want to achieve a miniaturized contact-free sensing system that will allow us to do imperceptible biomonitoring. So for the past 3 years, we have been working on this system. And what we did is trying to integrate a miniaturized radar system with RF radio frequency metamaterial, so that we can achieve highly directive radio frequencies signal propagation and collection, and also be able to achieve miniaturized data acquisition system. So with all that, what we hope to achieve is we can mount the device on top of our clothes instead of onto the skin, or we can mount the devices onto other parts of our wearable devices, such as the eyeglasses, right? So, and to achieve that, we have to make sure our antenna is effective enough, because otherwise, with this tiny device and also with all the ongoing interferences outside in the room, our signal to noise ratio will be so low, and we will not be able to see any meaningful signal from the measurements. So that's why we have designed different types of metamaterials to fit different needs. For example, this like a localized surface plasma metamaterials. It has a high sensitivity, but usually it's much more localized. And for this kind of patch antennas, it covers a much larger area, but of course the sensitivity is generally is less. So, and the reason to do this is to enable us to sense the skin vibrations in a non-contact way from different body locations. Like for example, with the LSP, it's better suited for a small tiny area and with small vibrations, and that's where we put it. Why we put it onto the eyeglasses frames to pick up the vibrations on our on the side of our head. And for these patch antennas, it easily goes onto the chest, right? Because when we breathe, the chest vibration amplitude is quite large, but it actually can cover a quite large area. So with this kind of designs, we will be able to accurately capture its biological information from different body locations, including the heart rate and heartbeat, and also the respiration rate. And the capability of measuring the physiological information from different body locations also enables us to calculate the pulse transit time, for example, from our chest to our limbs. And this actually is highly correlated with blood pressure. So by doing that kind of measurements, we will be able to achieve more sensing modalities. And also here is an example how we achieve sleep monitoring without skin contact. By just putting the devices on above the pajamas, we will be able to capture this kind of vital signs continuously during sleep. So yeah, I think so we still have 5 minutes. 5 minutes, yeah. So I'll briefly introduce some of our more recent works on sustainability, because if you look at all these wireless health sensors, you will notice that for some, you will notice that actually their form factor is not that small. Or in all of them, you will notice a bulky region. That's actually battery, right? So we need batteries to drive all these devices. And so far, all batteries are rigid. So that's why you see all the softenings in those devices, but they always have a region that looks very rigid. And so currently, you can make everything soft and flexible, but battery is the bottleneck. How we can make flexible energy storage devices actually is the question we need to address if we want to achieve fully flexible electronics. So, but it's actually very difficult because for all energy storage devices, we experience the issues of uneven electrochemical reaction from uneven interfaces, right? And that's what leads to dendrites, and that's what leads to short circuit inside the battery or reduce lifetime. Conventionally, people have done a lot in the field. Have done a lot to improve the performance of rigid batteries, and focusing on the electrical design and also electrolyte optimization. But the problem is this kind of interface strategies are prone to fail when it comes to flexible systems, because if such a system relies on interface, but when you are doing bending and all kinds of deformations, the interface will change, and it will reduce the effectiveness of such strategies. So, we really need some other strategies that will still stay effective during active continuous deformations. My group, in the past few years, we have been thinking about this, and one thing we found interesting is instead of using electrical field that's commonly implemented in all previous designs, why not just use a magnetic field? Because all the electrical depositions, they are charged ions. And with charged ions, if there's a magnetic field and the ion trajectory cuts through it, you get Lorentz force. And this Lorentz force actually can do the magic of regulating this uneven electron deposition. So here, I just show some results we noticed. So for this like planetary electrodes, right? So without magnetic field, you most likely it will be much quicker for you to get these kind of dangerous structures, like what you see here. But with the magnetic fields on the anode side, you see this more layered electrical surface after cycling. And this is a this is the cycling test. We can see clearly with the magnetic field, the cycling performance is much better than the case without a magnetic field. And there are actually 40 years ago, there are researchers who have studied the effects of magnetic field on batteries, but there are not so much progresses afterwards. Because one reason we suspect is that previously people are trying to use rigid large magnets to report that, and we actually experiment different magnetic fields and figured out that you only need a tiny magnetic field to make it effective, like about 50 millitesla. So you do not require rigid magnets. You can use small, tiny magnetic microparticles together with this kind of flexible batteries, and so that it will not affect the compliance of the your batteries, right? So another thing I would like to mention is that it also regulates the cathode behavior. You can see much more much less distortion in the crystal structure of the cathode material, which is magnesium oxide here. All right. So let's just to first implement this strategy into soft robot, because we found it quite interesting, because we need to have a magnetic field anyways, right? So this magnetic field naturally it exists in magnetically actuated soft robot. So it's already there. So we just put a flexible battery onto it and integrate them into a vertical form. Then by rationally design the circuit boards, we can achieve a fully flexible large area soft robot. And that gives us more intelligence in the robot. It will be able to sense, it will be able to sense the environment. It will be able to sense its own motions so that it can do perturbation corrections automatically. Okay, so based on the motion sensing powered by the onboard flexible battery, it will be able to perform the correction, coming back to the original trajectory and continue moving forward. Yeah. Okay. So, and we found it even more interesting on cylindrical electrode on fiber batteries or battery fibers, because wait, not. Oh, Yeah. So for cylindrical electrodes, we can see it used to be you can have the depositions on the top surface, which closer to the other electrode, and the large area of the backside of the electrodes are not effectively used. But with this kind of Lorentz force, more ions can be migrated to the backside of the electrodes, which greatly reduces the dangers on the right side. And also, it actually, you can see on the red plot there, because of the enhanced use of the active material on the cathode side, we can also see the capacity changes when we alternating the magnetic field on off. So this is because we are introducing more effective use of the entire surface of such fiber electrodes. And to implement such a strategy into a wearable form, then we use this kind of fiber extrusion design process. So on the inside is an electrochemical core with the batteries, electrochemistry inside, and on the outside we just use the micromagnet infused elastomer shell. So it's still soft, but it has the micromagnets inside it, and after magnetization, you will have remnant magnetic field in the fiber, and this magnetic field will greatly enhance the performance of electrochemical fiber inside of it. And from there, more interestingly, actually, when you are bending it, because of magnetoelasticity property, so basically when you are bending, this kind of magnetic particles become closer. And when they become closer, you are increasing the magnetic field. And by increasing the magnetic field, you can imagine we are increasing the Lorentz force that's driving these ions away from this kind of protruding areas, right? So it's actually effectively increasing the regulation performance there. So we can see as we increase the curvature, bending deformation, we can see the ratio of enhancement actually is increased here. Okay, so that's how we can achieve a pretty robust fiber battery. You can bend it, the voltage still stays stable. You can twist it, and you can punch it. Okay, and you can put it because of the elastomeric encapsulation. You can also it's some sort of waterproof. Of course, with the external magnetic field, you can do energy harvesting. You can have using electric induction, and because of by monitoring the magnetic field variation from outside the fiber, you will be able to sense the deformation of the fiber. And this also enables us to do intelligent battery monitoring, the management system. So when the battery is bent to a certain threshold, we just stop the powering from the battery to protect it, right? So more interestingly, we can integrate it with a Hall sensor, right? So wireless magnetic sensor. So this magnetic sensor can be powered by the fiber itself. And any deformation from the fiber itself will generate a varied magnetic field that's going to be sensed by the magnetic sensor powered by itself. So by mounting it onto different body locations, then we will be able to achieve self-powered or self-sustainable biomonitoring, either it's pulse, respiration, or gestures. So to summarize, we try to address the deformation demand tolerance imbalance between wearable devices, especially the electromechanical fiber and the electrochemical fiber, by using this kind of mechano-electrochemical design. So basically, you have a electrochemical core, you have a mechanical shell, and this allows us to regulate the electrochemical performance when it comes to deformation. So with the magnetic field, the performance can be greatly improved. And with this magnetic shell, we can also achieve multi-functionality inside a single fiber, from energy harvesting to storage to sensing. Well, I'm sorry it took me so long to cover the contents here. With all that, I would thank to my group members and all my collaborators and the funding agencies. Thank you so much.